Okay, so today we will be discussing elementary matrices and using those matrices to find inverse of a matrix, right? Same concept, if you remember from your FSC, you might have found inverse of a matrix by using row operations. If you remember, what do we do? Finding inverse of a matrix, usually by using row operations, we write matrix A here, whose inverse need to be found, and we augment that matrix with identity matrix. If you remember, that's what we said here. And then we convert this matrix into a reduced echelon form. Okay, and after converting this into reduced echelon form, we get what? If you remember, we discussed in last lecture that reduced echelon form of a non-singular square matrix is identity matrix. I hope you remember that. So if you convert this matrix into reduced echelon form, matrix A will be converted into identity matrix, whereas the same operations will apply on the identity matrix as well, because we have augmented these two matrices together. So we will get inverse of that matrix here. You might have done this thing in FSC, but now we do the same thing a bit in a different way. We consider that and discuss that in a different way. Otherwise, the steps will be same. Okay, so we already defined elementary row operations. If you remember, multiplying any row by a non-zero constant, the same thing you can divide it by a non-zero constant. You can interchange any two rows, right? And third one is adding a constant multiple of one row to another. And the same thing can be done for negative one as well. Okay, once you have these three operations, these three are automatically covered by these two, because if you say multiplying by C or dividing by C, so dividing by C basically means multiplying by 1 over C. Okay. So then we talked about equivalent matrices as well. If the two matrices are said to be equivalent if they are obtained by applying any of the row operations. If we apply one row operation on a matrix, you get another matrix, the two matrices will be row equivalent. You might know that there are three terms usually used in for this similar concept in matrices. One is equal matrices, the second one is equivalent matrices, and third one we'll be discussing later on, that is known as similar matrices. By word, they might look similar because we are using equal, similar, and equivalent for the same thing almost. But in matrices, they are different things. Equal matrices basically mean the corresponding entries should be same. Equivalent basically means two matrices will be equivalent if they are obtained by applying any of the row operations. And what are similar, we'll be discussing that later. Okay. Right. Now we come towards elementary matrix. What is elementary matrix? If we take identity matrix of any order, 1, 0, 0, 0, 1, 0, 0, 0, 1. If that is the identity matrix and we apply only one row operation on it, whichever, but applying only one row operation. If you interchange two rows, let's suppose row number 1 and row number 3, this becomes 0, 0, 1, 0, 1, 0, 1, 0, 0. You see, we interchange first and third rows. This matrix is known as elementary matrix. This is known as elementary matrix. Any matrix, in other words, we say that a matrix which will be converted into identity matrix by applying only one row operation. Any of the row operations, but only once. If you apply one or single row operation on a matrix and that give you identity matrix, that will be the elementary matrix. Or if you say, if you apply one row operation on identity matrix, then the matrix obtained will be elementary matrix. Okay. So what is the purpose of basically elementary matrix? You see, if we have a matrix, let's suppose that is 1, 2, and 3, 4, 5, and 6, 7, 8, and 9. And we apply row operation on it, the interchange row number 1 with row number 3. So physically we do that, it's 7, 8, 9, 4, 5, 6, 1, 2, and 3. But what did basically we do mathematically? We interchange two rows, row number 1 and row number 3, but in fact we multiplied this matrix by what? By identity matrix. You see, 0, 0, 1, 0, 1, 0, and 1, 0, 0. You multiply this matrix with the given matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. You see, this is the elementary matrix which was obtained by interchanging first and third row of identity matrix. And if you multiply this matrix with a given matrix, what would happen? The resulting matrix will be what? There will be automatically the two rows will be interchanged. You see, if you multiply it, what happens? You get 7. This with this one, so 8, 9. And if you multiply second row with this one, we get 4, 5, 6, 1, 2, 3. So basically, interchanging two rows of the matrix means you are multiplying that matrix by what? By the corresponding elementary matrix. So in fact, converting a matrix into echelon form or a reduced echelon form, what are we doing? We are multiplying that matrix every time by an elementary matrix. That elementary matrix could be obtained, you might have obtained by using interchanging row operation, multiple of a constant operation, or addition of a multiple of one row to another row operation. Right? So we basically do what? By applying that row operation, we are multiplying the given matrix by corresponding elementary matrix. These are some examples of elementary matrices. Listed below are 4 elementary matrices and the operations that produce them. The first one is, you see, multiplying third row of identity matrix by -3. We have 1 0 and 0 0 1, so we get 0 -3. Which operation is applied? Second row is multiplied by -3. This is elementary operation. Okay. In this case, second row and third row are fourth rows are interchanged. Right? So this is again an elementary matrix, which is obtained by what? Interchanging the second and fourth row of identity matrix. And in this case, three times of third row is added to first row. That is row number 1 plus 3 times row number 3. And in this case, we are having identity matrix. So identity matrix is itself an elementary matrix because you can multiply any of the row by 1. You multiply first row by 1 or second row by 1 or third row by 1, it will remain the same. So identity matrix is also an elementary matrix.
Excuse me, sir.
Yeah.
सर आइडेंटिटी मैट्रिक्स पर हम अगर कोई भी रो ऑपरेशन अप्लाई कर रहे हैं तो वो एक एलिमेंट्री मैट्रिक्स बन जाएगा.
सिंगल टाइम एक बार अप्लाई करते हो
जी सर.
तो एलिमेंट्री मैट्रिक्स होगा.
हेलो सर.
जी जी.
सर ये जो थर्ड हमारे पास मैट्रिक्स है जिसमें लिखा है ऐड 3 टाइम्स द थर्ड रो ऑफ रो नंबर 3 टू द फर्स्ट रो. सर इसमें 3 टाइम ऐड करेंगे या 3 टाइम सब्ट्रैक्ट करेंगे?
ऐड कर रहे हैं ना.
तो सर फिर 3 0 हो जाएगा ऐड करने से. ये मुझे सर थोड़ा डाउट हुआ.
आइडेंटिटी मैट्रिक्स पे अप्लाई करना है ना आपने. आपके पास आइडेंटिटी
ओके सर,
मैट्रिक्स क्या होता है?
ठीक.
दैट इज 1 0 0 0 1 0. दिस इज आइडेंटिटी मैट्रिक्स 0 0 and 1. Now applying the row operation, row number 1 plus 3 times row number 3. So what would you get? 1 plus 0, that is 1. 0 plus 0, that is 1 0. And 0 plus 1, 0 plus 3, that is 3. And the rest will be remain same because you apply only one operation on it.
Okay sir, so then we get the elementary matrix.
You get this elementary matrix. If you want to get back the identity matrix, you would apply that operation row number 1 minus 3 times row number 3. Then you will get back the same matrix, this one.
Got it, sir.
So that's what I said. If you are given a matrix, you see this is a matrix which is elementary matrix. And how would you know it's elementary matrix? If you apply one operation on it, and that give you identity matrix. So this matrix will be then elementary matrix, right? Or you can check it other way around. You will take identity matrix, you apply some operation on it, and if you get this matrix, you would say, okay, it is an identity matrix, elementary matrix. Okay, so as I said earlier, if the elementary matrix E results from performing a certain row operation on IM, and if A is an M cross N matrix, then the product EA is the matrix that results when this same operation is performed on A. That's what I said earlier. If you multiply a matrix by elementary matrix, the corresponding elementary row operation will be performed in the given matrix as well. So basically, row operations in a matrix, that means multiplication by elementary matrices. This is an example, you see. So consider this matrix 1 0 2 3 2 minus 1 3 6 1 4 4 0, and consider the elementary matrix 1 0 0 0 1 0 3 0 1. What is it? Again, it is row number 3 plus 3 times row number 1. Right? This is elementary matrix. If you multiply this matrix with A, what would happen? You will get exactly the same operation in matrix A as well. That is row number 3 plus 3 times row number 1, which is this one. Right? This matrix E is basically results from adding 3 times the first row of I3 to third row, and this product is doing the same thing. The same matrix that results when we add 3 times the first row of A to the third row. This is something I explained earlier at the beginning of the lecture. Okay. Check this thing I explained earlier. You see, if you have obtained elementary matrix by this procedure, you will get identity matrix by this procedure again. You see, if you multiply row I by non-zero constant, you will get elementary matrix. And if you want to get back that identity matrix from elementary matrix, you will do what? You will divide that row by the same number. And if you have interchanged I and j rows of a matrix to get elementary matrix, you interchange the same rows again to get identity matrix back. If you have add C times row I to j for production of elementary matrix, you will subtract that multiple of ith row from j to get back identity matrix. The same process I explained earlier. If you want to get elementary matrix, you apply one operation on the identity matrix, and if you want to get the identity matrix back, so apply the reverse operation. If you have done R1 plus C times row 3, so you, for getting back identity matrix, you will do R1 minus C times R3. Whatever. These are some examples. 1001 by multiplying second row with 7 to get elementary matrix, this one, and then dividing the second row by 7 to get identity matrix again. So this is the process to get elementary matrix, and then you get the same thing. In this case, 1001 by applying interchanging two rows to get 0 1 1 0, and applying the same operation again to get back identity matrix. So this is elementary matrix, because after applying one row operation we get identity matrix back. If you take row number 1 plus 5 times row number 2 to get 15041, this is elementary matrix. To get back identity matrix, you will do what? Row number 1 minus 5 times row number 2 to get back the identity matrix. It was something I explained earlier, you see. Let me take attendance. And check your names here, right? I hope everyone name is there who is present in the class. Anyone who is present in the class but name is not in the list. Okay, so every elementary matrix is invertible. And obviously the inverse is also an elementary matrix. Can somebody tell me why every elementary matrix is invertible? Invertible means whose inverse exists. Can somebody tell me why is this? No, you don't know?
Sorry, sir.
You see, I explained earlier that if you apply one row operation, single row operation on identity matrix, you will get elementary matrix, right? So we have one elementary matrix in hand. Now, if you apply one row operation back on that elementary matrix, you will get identity matrix back. And today at the beginning, I said that if a matrix is a non-singular matrix, then its reduced echelon form will be identity matrix. So any matrix whose reduced echelon form is identity matrix, it will be non-singular. And any matrix which is non-singular is invertible. For example, if you consider this elementary matrix, you see it is an elementary matrix, right? Because we interchange the two rows. Now we find, if you want to find a reduced echelon form of this matrix, REF, so what would you do? You would simply apply the one operation row number 1, 2, and that give you 1, 0, and 0, 1, which is the identity matrix. And any matrix whose reduced echelon form is the identity matrix will be a non-singular. If you remember, I explained that in last lecture that a matrix whose echelon form contains 0 row or column is singular and it's non-invertible, right? And a reduced echelon form of every non-singular matrix is always an identity matrix. Okay? That's why we say that every elementary matrix is invertible, and the inverse is also elementary matrix, because by applying one operation on elementary matrix to convert that into reduced echelon form will automatically convert identity matrix into its inverse. Okay. If you consider this matrix again, 0, 1, 1, 0, and if you want to find inverse of this matrix, so we take 1, 0, 0, 1 here. We augment the given matrix. This is matrix, elementary matrix, and this is the identity matrix. Okay, so we convert this into reduced echelon form. So number 1 and 2 will be interchanged. This becomes 1, 0, 0, 1. We interchange the complete row now. 0, 1, 1, 0. So in this case, E inverse will be what? E inverse is again 0, 1, 1, 0, which is also an elementary matrix. Because if you multiply these matrices together, in this case, the matrix E is inverse of itself. 0, 1, 1, sorry, it's 1, 0, multiply by 0, 1, 1, 0. If you multiply them together, you will get what? You see 0 into 0 is 0 plus 1. 0 into 1 plus 1 into 0 is 0. 1 into 0, 0 into 1 is 0. 1 into 1 plus 0 into 0 is 1. And now if the product of two matrices is identity, they will be inverse of each other. So E inverse is what? That is the same matrix. This one, which is again an elementary matrix. You see, this is also an elementary matrix. So that's what we say here, that every elementary matrix is invertible, and the inverse of elementary matrix is also an elementary matrix. Is it right? So these are some equivalent statements. If A is an n class n matrix, then the following statements are equivalent. That is, all true or all false. You say A is invertible if Ax equal to 0 has only trivial solution. The reduced echelon form of A should be the identity matrix, and A is expressible as a product of elementary matrices. So all of them are what? These statements are equivalent. If A is invertible, if A inverse exists, in that case, the system has only trivial solution. It has no non-trivial solution because we'll be getting only unique solution. Is it right?
Yes, sir.
जाग रहे हैं या सो रहे हैं?
जाग रहे हो सर? यस सर, इधर है.
Okay. Now, how do we find inverse of a matrix? By using those elementary matrices or elementary row operations. I explained it earlier. that we augment given matrix with identity matrix, and then we convert it into echelon form, reduced echelon form, obviously. So we do what? You see, by using mathematics in that case, we have one matrix A, and the other augmented matrix is what? That is identity matrix. So we apply basically one operation on it, that is E1. One operation means multiplying it by one elementary matrix. Then we apply another one, so we multiply by another elementary matrix. It might be the same one, it might be a different one. Then we go for another one. Then we go for another elementary operation, which means multiplying by elementary matrix, and so on, so on. Let's suppose you applied, there are k elementary operations applied on A to get identity matrix. Okay, as I said earlier, that we augment a matrix A with corresponding identity matrix, and then we convert this into reduced echelon form, and reduced echelon form will be what? This will be converted into identity matrix, and whatever we get here, that is A inverse. So why will it be A inverse? That is what I'm explaining here. ये तो आइडेंटिटी में कन्वर्ट हो गया ना बिकॉज ऑफ रिड्यूस एचेलॉन फॉर्म, लेकिन ये जो मैट्रिक्स आइडेंटिटी है ये ए इनवर्स क्यों बनेगा, तो जरा देखिए इधर से, ये तो क्लियर हो गया ना. अप्लाइंग एलिमेंट्री रो ऑपरेशंस ऑन मैट्रिक्स ए, you are getting identity matrix, right? If I multiply this matrix by A inverse from the right, multiplying this by A inverse from right, what do we have? You are having all these elementary matrices, ek dot e2 and e1. I'm not writing all of them now. Into A multiply by A inverse equals identity matrix multiply by A inverse. Okay. Now you know that A multiplied by A inverse is identity matrix. So you see ek e2 e1, and then we get identity matrix here, because a matrix multiplied by its inverse give you identity matrix. And then we have here A inverse, because A inverse multiplied by identity matrix is the same A inverse. So you see that we apply the same operations which we applied on matrix A to get identity. If we apply the same elementary operations on identity matrix, you will get A inverse. So that's why I claimed earlier that if you convert this augmented matrix into a reduced echelon form, the first part will become obviously identity because the matrix is non-singular, and the second part, which is the identity, by applying the same operation, it will give you A inverse, and it is because of this one. It's all because of this multiplication. You see that. So that's what we have. A inverse is equal to applying all the elementary matrices on multiplying elementary matrices on identity or applying elementary row operations on identity to get A inverse. You see in this case, you can write in this form. So to find the inverse of an invertible matrix A, find a
Sir,
sequence of elements. Yeah.
sir, if we apply all the operations, अगर हमने उस पर इनवर्स बनाने के लिए मल्टीप्लाई किया है, तो एलिमेंट्री में हमने आपने बताया कि मल्टीप्लाई किया हो तो दूसरी तरफ डिवाइड करेंगे, तो सेम ऑपरेशंस अगर हम यूज करेंगे तो मतलब मल्टीप्लाई किया है तो डिवाइड करेंगे, उधर
नहीं,
ऐड किया है तो इधर
आप कुछ चीज़ें मिक्स कर रहे हैं। मैंने ये कहा था कि अगर आपने एक आइडेंटिटी मैट्रिक्स पे कोई ऑपरेशन अप्लाई किया तो आपके पास एक एलिमेंट्री मैट्रिक्स आ जाएगा, राइट? अगर एलिमेंट्री मैट्रिक्स से आप वापस आइडेंटिटी मैट्रिक्स लेना चाहते हैं, वापस यू वांट टू गेट आइडेंटिटी मैट्रिक्स बैक, तो फिर आपने उसका उल्टा देना होता है।
यस सर,
बात समझ आ गई ये बात?
जी सर,
यहाँ पे जो बात हो रही है वो ये है कि जो एलिमेंट्री ऑपरेशन आप ए मैट्रिक्स पे अप्लाई करते हैं टू कन्वर्ट दैट इनटू आइडेंटिटी मैट्रिक्स, वही ऑपरेशन आप अप्लाई करोगे आइडेंटिटी मैट्रिक्स पे टू गेट इनवर्स। ये
जी
दो
सर,
डिफरेंट चीजें हैं।
ओके सर, सही,
ये दो डिफरेंट चीजें हैं, ये वही चीज नहीं है। वहां पे हम एलिमेंट्री से वापस आ रहे हैं आइडेंटिटी पे, यहाँ पे हम ऐसा नहीं कर रहे हैं। यहाँ पे अगर कोई एलिमेंट्री मैट्रिक्स हम ए के साथ मल्टीप्लाई कर रहे हैं तो वही एलिमेंट्री मैट्रिक्स को मल्टीप्लाई करना है विद आइडेंटिटी मैट्रिक्स एज वेल।
ओके सर, सही,
ठीक है?
यस सर, समझ आ गया।
Okay जी, so to find the inverse of an invertible matrix A, find a sequence of elementary row operations that reduces A to the identity and then perform the same sequence of operations identity matrix to obtain A inverse. ये वही बात है जो मैं अभी बता दिया है। सीक्वेंस सेम रहेगा, ऐसा ना हो कि आप फिर इंटरचेंज करें, पहले वो करें फिर वो करें, नहीं, वही सीक्वेंस रख लें इसको। So let's do this example. Using row operations to find A inverse. What you have done in FSC, obviously. 1, 2, 3, 2, 5, 3, and 108. As I said earlier, we augment this matrix with identity. We take this matrix here and identity matrix to the right. You see in this form. Now we need to convert this matrix into reduced echelon form. So making these two 0, row number 2 minus 2 row 1, row number 1 2 row number 3 minus row number 1, and then we make this one 0 and this one 0 as well. Once you convert that into identity matrix, this matrix identity it was at the beginning, by applying the same operation throughout, whatever you applied here, you apply the same thing, because you got a single matrix now, which is augmented matrix. The last matrix, this will give you the inverse. This is this one, minus 40, 16, 9, 13, and so on. It will be what? It will be the inverse of this matrix. Is that right?
Yes, sir.
यस सर,
So if you want to know whether this matrix is invertible or not invertible, there are two ways to do it. One, if you know determinant, so you find determinant of it, and if it is 0, it will be singular and inverse doesn't exist. But sometimes you feel that finding determinant at the beginning is obviously, I don't do that, it's laborious or something. So you start doing the steps directly of finding inverse. So wherever you see that the left matrix, matrix A, has a 0 row or 0 column, anywhere you feel that the complete row or column becomes 0, you stop there and you would say inverse doesn't exist. You shouldn't proceed then. You see, in this case, the last row becomes 0. So it means it cannot be converted into identity matrix. So this matrix is singular and inverse doesn't exist. Yeah, in this case, we are going to check whether the system has only trivial solution or it has non-trivial solutions. For that, obviously, we'll check whether the system is singular or non-singular. Right? So check the coefficient matrix and convert that into echelon form. If the coefficient matrix has a 0 row in echelon form, it will be singular. Otherwise, it will be non-singular. Forget about it this moment about assignments. I'll be giving you assignment later on. So let's move to exercise 1.5 book and see if there is any question which is difficult. So we discussed all these things. So you need to check whether this matrix is elementary matrix or not. Apply one condition or one operation on it and see if the matrix can be reduced into identity matrix. So you see, if you apply operation row number 1, row number 2 plus 5 times row number 1, after one operation it becomes identity matrix. So yes, this is elementary matrix. What about this one, the second part?
So it's
Can we
also an
convert this
elementary
matrix
matrix.
into, sorry?
Yes, sir. It is an elementary matrix.
It is
Oh,
or it is
sorry,
not?
sorry, sir. No, it is not. It is not because it requires two row operations.
That's right. You need to apply two row operations to convert into identity matrix, so it is not elementary. This one is also not, because we got a 0 row in it and it cannot be converted into identity
Identity matrix.
matrix because it's a singular matrix. And what about part D?
So it's also not an elementary matrix.
So part D is not an elementary matrix.
Yeah, part D is not elementary matrix because
It requires more than one row operations to make it a identity matrix.
right.
Yes, sir.
If you divide row number 1 by 2 first and then you subtract row number 3 from row number 1, so it will become identity matrix. First one was elementary, the remaining are not elementary. Same thing, question number 2 as well. Decide whether each matrix below is an elementary matrix or not. Okay, find a row operation and the corresponding elementary matrix that will restore the given elementary matrix to the identity matrix. Right? But the same thing again. Which row operation would apply to convert this elementary matrix into identity matrix? And then restore the given elementary matrix to the identity matrix. Like in first case, row number 1 plus 3 times row number 2 will restore the elementary matrix into identity matrix. I hope you can do that. Same thing, question number 4 as well. In question 5, it says that in each part, an elementary matrix E and a matrix A are given. Write down the row operation corresponding to E and show that the product EA results from applying the row operation to A. So first you see that in part A, row 1 and row 2 are interchanged. Okay, that's the row operation you will mention. And then if you see E multiplied by A will give you the same thing. The two rows will be interchanged. What is the row operation in B? That is row number 3 minus 3 times row number 2. And if you multiply this matrix with matrix A, you will get the same row operation. And so on. The same thing in part E as C as well. That is same thing in question number 6 as well. In 7 and 8, use the following matrices, right? A, B, C, D, E, F. सेवन में कह रहे हैं कि find an elementary matrix E that satisfies the equation EA is equal to B. A से B कैसे आ रहा है? How do we get B from A? By applying elementary row operation. So you see that row number 1 and row number 3 are interchanged. So which elementary matrix will be? The same operation applied in identity matrix will give you elementary matrix. Do you understand what I'm saying?
सर ए के साथ 001 वो आइडेंटिटी मैट्रिक्स मल्टीप्लाई करेंगे तो
जी.
बी आएगा.
What you would do, it means कि आइडेंटिटी मैट्रिक्स ए पे कौन सा ऑपरेशन अप्लाई हुआ जिसे बी आता है. तो यहाँ पे आप देख लेंगे. यहाँ पर अगर आप देखें ये रो और ये रो, ये दोनों रोज जो है वो मैट्रिक्स बी में इंटरचेंज हो गए. सी दिस रो एंड दिस, दे आर इंटरचेंज विद ईच अदर. ठीक है ना. तो वही ऑपरेशन जो आप आइडेंटिटी मैट्रिक्स पे अप्लाई कर लें तो आपके पास वो एलिमेंट्री मैट्रिक्स आ जाएगा. बी और ए में क्या हो रहा है? अगेन द सेम थिंग. तो बी और ए के लिए भाई सेम एलिमेंट्री मैट्रिक्स होगा. ए और सी में क्या हो रहा है ये आप जरा पहले चेक करेंगे. व्हाट्स गोइंग ऑन इन सी एंड ए? द फर्स्ट रो इज सेम, second is same, something happened in third row. And what happened in third row from A? वो ऑपरेशन आपने देखना है. कौन सा ऑपरेशन अप्लाई हुआ यहाँ पे? So that is row number 3 minus 2 times row number 1. Let me introduce some commands so that you can write. How do we get this matrix from this one? Sorry. This from this. The first row is same, The second are same. There is a difference in the third row. So if you apply condition row number 3 minus 2 times row number 1, what would happen? 8 minus 6, that is 2. 1 minus 8 is minus 7. And 5 minus 2 is 3. This is the operation applied on matrix A to get C. Applying the same operation on what? Identity matrix. We take 1 0 0 0 1 0 and then 0 minus 2 0 and 1 minus 0. So that will be the corresponding elementary operation. You see, this is a elementary operation. And then how do we get A back from C? So that is row number 1 plus row number 1 plus row number 3. You get matrix A back. We are getting this elementary operation. Elementary matrix. Same thing in question number 8 as well. In 9 and 20 to 24, use the inverse algorithm to find the inverse of the given matrix, if exists. So by applying that method, let's find this one. Let me do question 9 here. We augment the matrix 1 4 2 7 with 1 0 0 1 to find inverse. Okay, so you convert this into echelon form, reduce echelon form. This is row equivalent to row number 2 minus 2 times row number 1. 1 4 1 0, 2 minus 2 0, 7 minus 8 minus 1, 0 minus 2 minus 2, and 1 minus 0 is 1 again. Now we need to make this one is 1. So row equivalent to minus 1 times row number 2. 1 4 1 and 0 0 1 2 minus 1. Now we make this one 0. So this is row equivalent to row number 1 minus 4 times row number 2. 1 minus 0 is 1. 4 minus 4 is 0. 1 minus 8. Minus 7. 0 plus 4 is 4. 1 2 and minus 1. So this is the inverse in this case. A inverse will be minus 7 4, 2, and -1, which is the required answer in this case. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Can you find the rest, inverse of the rest of the matrices?
Yes, sir.
Then in question 15, you would see there might be a 0 row in the echelon form, so you would say inverse doesn't exist. ये अपने क्वेश्चन नंबर 24 तक करना है. And then go to 28 is what? Same thing in question 5. To find the inverse of it, very simple. And 26, find the inverse, simple. And 27, it says find all values of C, if any, for which the given matrix is invertible. So you can do that by using row operations, or you can do that by determinant as well, right? Okay, so any question?
No, sir.
No. It's not updated. J. Akramullah.
सर मेरा नाम अटेंडेंस लिस्ट में नहीं है.
आप थोड़ा सा और भी लेट आ जाते ना.
सर लेट नहीं आया हूँ. सर सिर्फ 2 मिनट लेट आया हूँ सर.
अब ये बात मैं कैसे मान लूँ आपसे? आपके समय कैसे मान
सर
लूँ ये
मैंने
बात?
लिंक सर मैंने लिंक 2 मिनट सर बाद तकरीबन ज्वाइन की थी सर.
तकरीबन अब 18 ना. मैंने अटेंडेंस कितने टाइम बाद ली थी?
सर 30 मिनट्स बाद.
30
सर
मिनट बाद
आधे
मैंने
घंटे
अटेंडेंस ली थी, और आधे घंटे में वो नहीं था. ठीक है ना. और उसके बाद भी अब ये 37 मिनट्स और भी हो गए हैं, और ये कह रहा है मैं 2 मिनट्स लेट था.
सर सीआर ने 8:30 पर का क्लास का कहा था सर, लेकिन 8:30 पर नहीं स्टार्ट नहीं हुई थी सर.
तो
सर फिर लेट हो गया थोड़ा सा सर. 2 मिनट 3 मिनट सर लेट हो गया, इससे ज़्यादा लेट नहीं हुआ.
2-3 मिनट लेट कैसे हुए मुझे आप बताएं ना. 30 मिनट लेट तो मैंने अटेंडेंस ली थी. इवन दो क्लास जब मैंने स्टार्ट किया उसके बाद क्लास में मैं कुछ लेट स्टार्ट की थी, 50 पे स्टार्ट की थी ना शायद.
Yes, sir. Around 50-55.
जी. और उसके बाद फिर आधे घंटे बाद मैंने अटेंडेंस अपडेट की थी, उसमें भी आप नहीं थे, और आप फिर भी कह रहे हैं कि मैं 2 मिनट. कौन से 2 मिनट्स आपके हैं? चलो पहले मैं आपसे रेफरेंस पूछ लूँ, क्योंकि फ्रेम ऑफ रेफरेंस इंपॉर्टेंट होता है ना. जो आपके 2 मिनट्स हो शायद आप हमारे लिए कोई 40 या 45 मिनट्स हो. असल में सिस्टम में सारा रिकॉर्ड मौजूद होता है ना, इशू ये होता है. Okay, just some more linear systems. I may get through it quickly because you should have learned that in FSC. All right. We had a discussion about system of equations, but we discussed the elimination method and Jordan method. So now we go for inversion method or Kramer rule. We say if in a system of equations coefficient matrix is invertible, then solution can be simply found by multiplying A inverse with the right hand side. Because if A inverse exists, you can simply multiply that to the inverse of the coefficient matrix to the right side to get solution. But these methods, the inversion method can be only applied in square systems. The number of equations and number of variables are same and the system is non-singular. Then you can apply this method. If an example, we have matrix A, coefficient matrix 1, 2, 3, 2, 5, 3, 1, 0, 8. Unknowns are x1, x2, x3, right side is 5, 3, 17. So we find inverse of this matrix by either method. You can apply whatever. We would first find determinant of this matrix. In fact, we found inverse of this matrix already a bit earlier by using those operations. And then we multiply this inverse with right hand side 5 to 17 to get solution 1 minus 1, 2. Sometimes we have same system of equations with different right hand side. The coefficient matrix remains same, only the right side are different. Right? So you can solve two systems together as well. You see, you augment, you see that's the left side is same. 1, 2, 3, 2, 5, 3, 1, this one, this one. We have these cases later on as well. So you do what? We consider coefficient matrix, then augment the right side of first system and the second system. And then we convert this matrix into reduced echelon form. Okay, so you see for first system the solution is 1, 0, 1. For a second system solution will be 2, 1, minus 1 if you convert that into reduced echelon form. Now these are equivalent systems. Again the same thing. Some terms are extended. If A is n class n matrix, the following are equivalent. A is invertible, obviously. If A is invertible, Ax equal to 0 is only trivial solution. The same thing we discussed earlier. The reduced row echelon form will be identity matrix. Yes, I discussed earlier. A is expressible as a product of elementary matrices. That's right. And Ax is equal to B is consistent for every n class 1 matrix, because if A is invertible, it will be obviously consistent. And it will be having exactly one solution. If a square matrix is invertible, in that case, the system will be having unique solution, because its reduced echelon form will be identity matrix. And then if you go back to those conditions I discussed, that if the last row is 0, then many solution. If last row of matrix A is 0, where B is not 0, no solution. And if both are, if that is not 0, तो वो फिर क्या होता है? यूनिक सोल्यूशन होता है. You don't need this thing. What condition must B1, B2, and B3 satisfy in order for the system of equations to be consistent? So it is the same thing. You convert that into row echelon form, and at the end you would make a decision. You see, when you convert that into reduced echelon form, we have 0, 0, 0, and this B3 minus B2 minus B1. This term is 0. Now, if this is 0, the system will be having solution, and if this is not 0, then you would say that the system has no solution. So we are asked to check whether it is has a solution or not. Okay, so we would be saying that the system has solution if this quantity is 0. So we could write b3 is equal to b1 plus b2. Again, we may have a free variable, so we take b1 and b2, and then b3 is what? That is b1 plus b2, where b1 and b2 are any arbitrary numbers. If you take b1 is 1, b2 is 1, so b3 must be 2. If you take this one 1, this one 2, so b3 will be 3 then, and so on. Same thing here. In this case, we have this quantity is 1, so the system will be having unique solution. अगर ये 0 होता तो फिर हम बात करते इस पे, ये 0 है या 0 नहीं है. लेकिन अगर ये नॉन 0 आ जाता है तो फिर तुमने बात की थी इस पे, the system will be having unique solution. We'll be using these things later on, right? We'll be considering arbitrary point A, B, C, or A1, A2, A3, or B1, B2, B3, and solving the system and then imposing condition on it that whether the system has unique solution or many solutions or no solution. Is it clear?
Yes, sir.
So then we move towards exercise 1.6 from question 1 to 20. It's a simple question. Solve the system by inverting the coefficient matrix. We take coefficient matrix, find the inverse, multiply to the right side. Okay, so this will be your assignment number 1. Exercise 1.5 from question number 1 to question number 20. Right? Let me introduce that assignment for you. Let's have assignment number 1. Get a document for you. Do question 1 to 20 of exercise 1.5. Do you know your class numbers? Is that okay?
Yes, sir.
Yes, sir.
Those students
सर
whose
जिनका
class
ओड रोल नंबर है वो ओड क्वेश्चंस करेंगे और जिनका इवन रोल नंबर में आता है वो इवन वाले क्वेश्चंस करेंगे.
G. क्लास का टाइम पे भी है ना तो
सॉरी सर क्या वो
सेक्शन बी वाले क्लास का पूछ रहे हैं अभी उनका क्लास का टाइम पे भी है. Okay. Sorry, was it exercise 1 point? It was 1.6, right? Sorry, let me make a change then. Yeah. मैंने क्या लिखा 1.6 या 1.5 लिखा है?
सर आपने
1.5
1.5 लिखा है.
1.5.
No, it says 1.6. Okay. Okay, so let's talk about some more systems or more matrices. A very simple diagonal matrix, triangular matrices and symmetric matrices. So, do you want me to discuss it for you, or you know yourself? You will do that. Okay, check it yourself. Very simple matrices, simple discussions, so on. Right, and then I do exercise 1.7 as well. I'll be talking about application of linear systems in next lecture, inshallah. ये आप देख लें, ठीक है. I'm presuming that you know diagonal matrices, upper triangular, lower triangular. You have done everything in FSC, so I'm not wasting my time here.
Okay, sir.
अभी बताएं किसी का नाम अगर मिसिंग है तो मुझे बताएं. Right. So if there is no question, so I may stop recording first and then